Theoretical probability. Used when all the events are equally likely to occur, such as games of chance. Empirical probability. Used for a series of trials that produce outcomes that cannot be predicted in advance, such as simulations. Experiment. The process of measuring or observing an activity for the purpose of collecting data. Outcome. A particular result of an experiment. Sample space. All the possible outcomes for the experiment. Event. One or more outcomes of an experiment. Law of large numbers. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. Equally likely. All events have an equal chance of occurring. Complement of event A. Event A not occurring. Disjoint. Two events that cannot occur at the same time. Not disjoint. Events that are overlapping and therefore can occur at the same time. Independent. When one event's occurrence does not affect the probability that the other event will occur, P equals P. Dependent. When one event's occurrence affects the probability the other event will occur. Conditional probability, P. Probability of event B occurring given that event A has already occurred. Probability tree. A display tool that is particularly useful for showing probabilities when the events occur in stages and conditional probabilities are involved. Two-way probability table. A display tool that is particularly useful for showing the four possible combinations for two categorical variables with two possible values. Volunteer sample. Participants must volunteer to participate, tends to increase bias. Convening sample. Participants are easy for researcher to access, tends to increase bias chosen because individuals were in the right place at the right time to suit the researcher, may be different from the general population in a subtle but important way. Sampling frame. Subset of population possibly in the sample individuals from whom the sample is actually selected should match the population of interest. Bias may result if parts of the population are systematically excluded. Sampling frame bias. If the sampling frame is not equal to the whole population, this may introduce bias. Population. The group you are trying to measure/describe. Sample. The group included in a study. Systematic sampling. Random sample. Every individual has equal probability of being selected. Volunteer response. Members of the sample may choose not to respond, similar to non-response. Non-response. The possibility that subjects in the sample do not respond to a survey, similar to volunteer response. Simple random sampling. Cluster sampling. Stratified sampling. Multi-stage sampling. Sample size. Number of people in the sample. Small samples introduce bias. Bias. Any systematic failure of a sampling method to represent its population. Probability sampling plan. Any system of selecting a sample from the sampling frame which involves the use of a random process. For example, simple random sampling, cluster, stratified, and multi-stage sampling. How do you calculate P? P equals of outcomes in a slash of outcomes in the sample space. The probability of an event occurring is between and 0 and 1. What is the sum of the probabilities of all possible outcomes? 1. P equals 1P. For disjoint events, P equals P plus P. For non-disjoint events, P equals P plus P, P. For independent events, P equals PP. For dependent events, P equals PP. For disjoint events, P equals 0. For dependent events, what relationship does P have with P? Not equal. For independent events, what relationship does P have with P? Equal. P equals P slash P. Two steps to producing data are blank in study design. Sampling. It is essential that the blank be truly representative of the largest population. Sample. Studies should be designed to discover what we want to know about the variables of interest for individuals in the blank. Sample. Blank does not imply causation. Correlation. A sample that produces data that is not representative because of the systematic under- or overestimations of the values of the variable of interest is called blank. Bias. Blank may result from either a poor sampling plan or from poor design for evaluation variable of interest. Bias. Blank is where individuals have offered to participate in the study. Volunteer sample. A blank is almost guaranteed to be biased because participants tend to be comprised of individuals who have a particularly strong opinion about an issue and are looking for an opportunity to voice it. They may also be motivated to participate out of desperation. Volunteer sample. A blank is sometimes the only ethical way to obtain a sample. Example: medical studies. Volunteer sample. A blank sample is where individuals happen to be at the right time and place to suit the schedule of the researcher. Convenience. Posting a music lover survey on a university internet bulletin board and asking students to vote for their favorite type is called a blank. Volunteer sample. Standing outside the student union and asking students passing by to respond to your questions about music preference is a blank sample. Convenience. A convenience sample may also be susceptible to blank because certain types of individuals are more likely to be selected than others. In the extreme, some convenience samples are designed in such a way that certain individuals have no chance at all of being selected. Bias. Ask your professors for email rosters of all the students in your classes, randomly sample some addresses, and email those students with your question about musical preference. In this case, the roster is considered a blank. Sampling frame. Blank lists potential individuals to be sampled and may not match the population of interest. Sampling frame. Sampling frame can introduce blank because the sampling frame may not match the population as closely as possible. Bias. Obtain a student directory with email addresses of all the university students and send the musical to every 50th name on the list is an example of blank sampling. Systematic. The safest way to avoid bias is to use blank sampling. Random. Blank sampling is when individuals are sampled completely at random and without replacement, then each individual is equally likely to be selected. Simple random sample.
Obtain a student directory with email addresses of all the university's students and send your music poll to a randomized subset as an example of blank. Simple random sample. In an SRS, suppose only 40% of people send back their votes. This study potentially has bias from non-response and blank. Volunteer response. A simple random sample is a blank way to base a selection on randomness. Easiest. A blank is the simplest probability sampling plan. It is equivalent to selecting random names out of a hat, where each individual has the same chance of being selected. Simple random sample. Blank sampling is sampling technique is used when a population is naturally divided into groups. This technique includes some of the groups in their entirety. Cluster. In blank sampling, we take a random sample of groups and use all the individuals within the selected clusters as our sample. Cluster. In order to get a sample of high school seniors from a certain city, you choose 3 high schools at random from among all the high schools in that city and use all the high school seniors in the 3 selected high schools as your sample. This is an example of blank sampling. Cluster. Blank sampling is used when our population is naturally divided into groups. This technique ensures that each of the sum of the groups is equally represented. Stratified. All the students in a certain college are divided by gender or by year in college. All the registered voters in a certain city are divided by race or examples of blank. Groups. In blank sampling, we choose a simple random sample from each group, and our sample consists of all these simple random samples put together. Stratified. In order to get a random sample of high school seniors from a certain city, we choose a random sample of 25 seniors from each of the high schools in that city. Our sample consists of all these samples put together. This is called a blank sample. Stratified. In blank sampling, we take a random sample of groups and include every individual from those groups. Cluster. In blank sampling, we take a simple random sample of every group. Stratified. Blank sampling is a complex form of cluster sampling. Multistage. Blank refers to individuals who do not go along with the researcher's intention to include them in a study. Non-response. If there are too many non-respondents and they are different from respondents in an important way, the sample may have blank. Bias. Blank sampling makes the sampling process more manageable by working down from a large population to successively smaller groups within a population, taking advantage of stratifying or clustering along the way, and often finishes up with either a cluster sample or a simple random sample. Multistage. A blank sampling plan will result in a non-biased sample, which can be safely used to make inferences. Probability. The entire group of individuals to be studied is called a blank. Population. A blank is a person object that is a member of the population to be studied. Individual. A blank is a subset of the population that will be studied. Sample. Selecting every 8 from a list is an example of blank sampling. Systematic. Blank is the number of participants in a study and determines the accuracy of the predictions we make based on surveys. Sample size. The larger the blank, the more accurate the survey. Sample. Observational study. A blank is where values of the variable of interest are recorded as they naturally occur. There is no interference by researchers who conduct the study. Sample survey. A blank is a particular type of observational study in which individuals report variable values themselves, frequently by giving their opinions. Perspective. A blank study is a study where values of interest are recorded forward in time. Retrospective. A blank study is a study where values of interest are found in existing historical data. Two-way table. In both observational studies and experiments where both explanatory and response variable are categorical, we can record the data in a blank. Response. The blank variable is the observation or measurement made by the researcher. Lurking/confounding. One way to establish a causal relationship between the explanatory and response variable is to eliminate the effects of the blank variables. Lurking. The existence of a virtually unlimited number of potential blank variables is the reason why we cannot establish causation based on an observational study. Randomized controlled experiment. Blind. A blank study is a study in which the subjects are unaware of which treatment is being administered to them. Placebo effect. When patients improve because they believe they are receiving treatment even though they are not actually receiving treatment, this is known as the blank. Explanatory effect. It is important for researchers who evaluate the response to be unaware of which treatment the subject received in order to prevent the blank from influencing their assessments. Double-blind. If neither the subjects nor the researchers know who was assigned what treatment, then the experiment is called blank. Hawthorne effect. The phenomenon whereby people in an experiment behave differently from how they would normally behave is called the blank. Lack of realism. Blank is a possible drawback to the use of an experiment rather than an observational study to explore a relationship. Non-compliance. Blank is failure of the subject to submit to the assigned treatment. Randomization. The most vital stage for blank in an experiment is during the assignment of treatments rather than the selection of the subjects. Experiment. Depending on the variables of interest, researching the relationship via and blank may be too unrealistic, unethical, or impractical. Conditional percentages. Raw data from a two-way table can be made more useful by computing blank. Factors. Explanatory variables are also called blank. Random. In order to gain optimal information about individuals in all various treatment groups, we would like to make assignments that are blank and even. Blocking. An experiment's design may be enhanced by relaxing the requirement of total randomization and blank the subjects first. Match pairs. Blank may enable us to pinpoint the effects of the explanatory variable by comparing responses for the same individual under two explanatory values, or for two individuals who are as similar as possible except the first gets one treatment and the second gets another. Bias. One way to test for blank in a survey question is to ask yourself, just from reading the question, would a respondent have a good idea of what response the surveyor is hoping to elicit? If the answer is yes, then the question should have been worded more neutral. Randomized response. A blank allows individuals in the sample to answer anonymously, while the researcher still gains information about the population. Influence. Earlier questions should not deliberately blank responses to later questions. Honest. Survey methods and questions should be carefully designed to elicit blank responses if there are sensitive issues involved. Explanatory. The blank variable is the one researchers will point to as the causal explanation for what is observed. Observational study. A study where the participants are self-assigned and researchers only observe. Prospective study. A type of observational study where the values of the variables of interest are recorded forward in time as they happen. Retrospective study. A type of observational study where the values of the variables of interest are recorded backward in time using the available history. Experimental study. A study where the researchers assign the participants to various treatment groups and then the researchers observe. Causation. The idea that the variation in the response variable is caused by changes in the explanatory variable. The key to establishing causation is to rule out the possibility of any lurking variable. Lurking variable. A variable in a study which is not examined, but which may be related to the explanatory and/or response variable. Explanatory variable. A variable in a study which is being proposed as a cause and it is manipulated to observe a response in other variables. Response variable. The variable in a study which is measured or observed. This variable changes as a result of the manipulations to the explanatory variable. Factor. Another word for the explanatory variable. Treatments. The different imposed values of the explanatory variable. Treatment groups. The groups receiving different treatments. Control group. Those individuals on whom no specific treatment was imposed used to rule out lurking variables. Subjects. Human participants in a study. Randomized controlled experiment. Blind experiment. An experiment where the subjects are unaware of which treatment is being administered to them, if any. Placebo. Benign treatment given to the control group so that there are no psychological differences between those who receive the drug and those who do not. Placebo effect. When the response variable changes because the subjects are told they are receiving treatment even though they are not actually receiving treatment. Experimenter effect. When the response variable changes because the experimenter is aware of whether or not a treatment is being given to the subject. Double-blind experiment. An experiment where the subjects and experimenters are unaware of which treatment is being administered, if any. Hawthorne effect. A phenomenon where people in an experiment behave differently from how they would normally behave. Non-compliance. This describes when subjects fail to submit to the assigned treatment. Blocking. Match pairs. A method where the experimenter attempts to pinpoint the effects of the explanatory variable by comparing responses for the same individual under two explanatory values, or for two individuals who are as similar as possible except that the first gets one treatment and the second gets another. Open question. This type of question allows for almost unlimited responses. The participant can phrase their answer any number of ways. Closed question. This type of question allows for only a few responses. While it allows for easier analysis of the study, it may influence how a person answers a question, introducing bias. Leading question. This type of question is worded in such a way as to guide the participant to a particular answer, introducing bias. Complicated question. This type of question is worded in such a way that it may confuse or frustrate the participant, introducing bias. Neutral question. This type of question is worded in such a way that it fairly and objectively presents the question, does not introduce bias. Randomized response. To minimize response bias for sensitive questions, the individuals answer the question anonymously. Various methods can then be used to estimate the sample's response in aggregate without the researcher knowing an individual's answer. The mean of a set of data is 14 and the standard deviation is 2. Suppose the distribution is normal. What percent of the data is between 12 and 16? 68%. The mean of a set of data is 14 and the standard deviation is 2. Suppose the distribution is normal. What percent of data is between 8 and 20? 99.7%. The mean of a set of data is 14 and the standard deviation is 2. Suppose the distribution is normal. What percent of data is less than 12? 16%. The mean of a set of data is 14 and the standard deviation is 2. Suppose the distribution is normal. What percent of data is larger than 18? 2.5%. The mean of a set of data is 14 and the standard deviation is 2. Suppose the distribution is normal, then 16% of the data is larger than what number? 16. The mean of a set of data is 14 and the standard deviation is 2. Suppose the distribution is normal. What percent of the data is greater than 10? 97.5%. The mean of a set of data is 100 and the standard deviation is 20. Suppose the distribution is normal. What percent of the data is between 60 and 140? 95%. The mean of a set of data is 100 and the standard deviation is 20. Suppose the distribution is normal. What percent of the data is between 80 and 120? 68%. The mean of a set of data is 100 and the standard deviation is 20. Suppose the distribution is normal. What percent of the data is less than 140? 97.5%. The mean of a set of data is 100 and the standard deviation is 20. Suppose the distribution is normal. What percent of the data is larger than 80? 84%. The mean of a set of data is 100 and the standard deviation is 20. Suppose the distribution is normal, then 16% of the data is larger than what number? 120. The mean of a set of data is 100 and the standard deviation is 20. Suppose the distribution is normal. What percent of the data is larger than 160? 0.15%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, then 99.7% of the data is between what values? 15 and 33. The mean of a data set is 24 and the standard deviation is 3. 68% of the data is between what values? 21 and 27. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, then 95% of the data is between what values? 18 and 30. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is larger than 21? 84%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is less than 21? 16%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is larger than 18? 97.5%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is less than 18? 2.5%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is larger than 15? 99.85%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is less than 15? 0.15%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal, what percent of the values is larger than 27? 16%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal. What percent of the values is less than 27? 84%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal. What percent of the values is less than 30? 97.5%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal. What percent of the values is larger than 30? 2.5%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal. What percent of the values is larger than 33? 0.15%. The mean of a data set is 24 and the standard deviation is 3. Suppose the distribution is normal. What percent of the values is less than 33? 99.85%. Number of cigarettes smoked per day. Quantitative. Grade point average. Quantitative. A person's occupation. Categorical. Marital status. Categorical. A person's height. Quantitative. Number of children in a family. Quantitative. Type of newspaper read. Categorical. Hair color. Categorical. Pulse rate. Quantitative. Size of a car's gas tank. Quantitative. Weight. Quantitative. Computer skill level. Categorical. The number of words per minute that a person can type. Quantitative. The level of lead in water. Quantitative. First letter of your last name. Categorical. Serum cholesterol. Quantitative. Outcome when tossing a coin. Categorical. Letter grade in a course. Categorical. Number of goals scored in a hockey game. Quantitative. Time. Quantitative. Categorical variable. Variable with category or labeled values. Example, gender male or female. Quantitative variable. Variable that can be measured numerically. Example, distance, weight, dollar amounts. Pie chart. A graphical display of categorical data that relates each category to the whole, used for one categorical variable. Bar chart. A graphical display of categorical data that compares the categories to each other, used for one categorical variable. Histogram. A graphical display of one quantitative variable. The horizontal axis has the data values broken into bins and the vertical axis has frequency counts. Stem plot. Sometimes called stem and leaf plots, used to organize one quantitative variable. Leaves consist of the rightmost digit of the number. The stems are the rest of the number. Box plots. Used to display one quantitative variable. The data is sectioned into quartiles. A box is drawn around the interquartile range and whiskers are drawn to represent the range of the upper and lower quartiles. Mean. Average, found by adding all the data together and dividing by the number of data points. Median. Middle, found by putting the numbers in order and choosing the value that best represents the middle. Mode. The number that occurs most often. Outliers. Observations that fall outside the overall pattern. Range. Measure of spread, highest value, lowest value. Interquartile range IQR. Range of the two interquartiles Q3, Q1. 5 number summary. Numerical version of the box plot consists of minimum Q1, median Q3, and maximum. Standard deviation. Measure of spread describes how far data are on average from the mean. Standard deviation rule. Only works if the data have a normal distribution. 68% of the data lies within one standard deviation of the mean, 95% of the data lies within two standard deviations of the mean, 99.7% of the data lies within three standard deviations of the mean. C greater than Q. A study in which the explanatory variable is categorical and the response variable is quantitative. Best graphical display to use in such a case, side-by-side box plots. C greater than C. A study in which the explanatory variable is categorical and the response variable is categorical. Best display to use in such a case, a two-way table or a contingency table. Q greater than Q. A study in which the explanatory variable is quantitative and the response variable is quantitative. Best graphical display to use in such a case, a scatter plot. Correlation coefficients are measures the strength and directionality of a linear relationship between two quantitative variables. Should not be used for non-linear relationships. Linear regression. The process of fitting a line to a scatter plot. Linear regression equation. Extrapolation. Plugging in a value of the explanatory variable which is outside the domain of values for the explanatory variable in a given data set in order to predict the value of the response variable. Association. The mathematical relationship between two variables. Correlation. The mathematical relationship between two quantitative variables. Simpson's paradox. When an extra variable is included which appears to fundamentally change the nature of an association between the two variables of interest, we can never be 100% certain of a claim of causation based on observational study, so cannot draw causal conclusions when using observational study. Observational studies are an extremely common tool used by researchers to attempt to draw conclusions about causal connections. It is difficult, or perhaps even impossible, to establish causation in an observational study. Especially due to the problem of lurking variables, the key to establishing causation is to rule out the possibility of any lurking variable, or in other words, an experiment is when researchers determine the values of the explanatory variable of interest for the individual study, rather than letting them choose when to generalize results we find in a sample to the entire population. Only if the subjects were selected at random can we make such a generalization. Whether or not we can draw causal conclusions does depend on how the selected subjects were divided into the four shampoo group. It must be random to control for lurking variables. Determine whether the explanatory variable is actually causing changes in the response variable. To carry out a randomized controlled double-blind experiment. In a blind experiment, the subjects are not aware of which treatment is administered to them. Placebo is probably administered to the control group. Observational studies. Experiments. Blocking the subjects. Split the sample subject into blocks based upon the different values of the background variable and then randomly allocate treatments within each block. Gender male, female, size small, large. A sample survey is a type of observational study in which respondents assess variable values. Open questions are less restrictive, but responses are more difficult to summarize. Closed questions may be biased by the options provided. Closed questions should permit options such as other and or not sure if those options may apply. Questions should be worded neutrally. Earlier questions should not deliberately influence responses to later questions. Questions shouldn't be confusing or complicated. Survey methods and questions should be carefully designed to elicit honest responses if there are sensitive issues involved. Observational studies, it is difficult to establish convincing evidence of a causal relationship because of lack of control over outside variables. Experiments allow researchers to take control of lurking variables by randomized assignment to treatments, which helps provide more convincing evidence of causation. Sample surveys are occasionally used to examine relationships, but often they assess values of many separate variables, such as respondents' opinions on various matters. Survey questions should be designed carefully in order to ensure unbiased assessment of the variable values. What are the two simple graphical displays for visualizing the distribution of categorical data? The pie chart, the bar chart. The distribution of a categorical variable is summarized using graphical display, pie chart or bar chart, supplemented by numerical summaries, category counts, and percentages. A variation on pie charts and bar charts is the pictogram. Pictograms can be misleading, so make sure to use a critical approach when interpreting the information the pictogram is trying to convey. The square bracket means including and the parenthesis means not including. For example, 50, 60 is the interval from 50 to 60, including 50 and not including 60, 60, 70 is the interval from 60 to 70, including 60 and not including 70, etc. It really does not matter how you decide to set up your intervals, as long as you're consistent. When data are displayed in a histogram, shape. When describing the shape of a distribution, we should consider symmetry, skewness of the distribution, peakness, the number of peaks the distribution has, a skewed right histogram, a skewed left histogram. Note that skewed distribution can also be the middle. More than two modals. Multimodal. The center of the distribution is its midpoint. The value that divides the distribution so that approximately half the observations take smaller values and approximately half the observations take larger values. The spread of the distribution can be described by the approximate range covered by the data. The histogram is a graphical display of the distribution of a quantitative variable. It plots the number of observations that form intervals of values. When examining the distribution of a quantitative variable, one should describe the overall pattern of the data and any deviations from the pattern. Not all distributions have a simple, recognizable shape. Outliers are data points that fall outside the overall pattern of the distribution and need further research before continuing the analysis. It is always important to interpret what the features of the distribution mean in the context of the data. The skim plot is another graphical display of the distribution of quantitative data. The leaf is the rightmost digit. The stem is everything except the rightmost digit, so if the data point is 34, then 3 is the stem and 4 is the leaf. If the data point is 3.41, then 3.4 is the stem and 1 is the leaf. The stem plot has additional new features. It preserves the original data. It sorts the data, easy and quick to construct for small, simple data sets. The mode is the most commonly occurring value in a distribution. The mean is the average of a set of observations. If the n observations are x1, x2, xn, the mean, which we denote by xx, is therefore x equals x1 plus x2 plus xn, and x equals x1 plus x2 plus xn, and the mean is very sensitive to outliers. The median n is the midpoint of the distribution. It is the number such that half of the observations fall above and half fall below to find the median. The mean describes the center as an average value, in which the actual values of the data points play an important role. The median, on the other hand, locates the middle value as the center, and the order of the data is the key to finding it. For symmetric distributions with no outliers, x is approximately equal to m. For skewed right distributions and/or data sets with high outliers, x greater than m greater than. For skewed left distributions and/or data sets with low outliers, x less than m less than. The mean is an appropriate measure of center only for symmetric distributions with no outliers. In all other cases, the median should be used to describe the center of the distribution. The three most commonly used measures of spread: range, interquartile range, standard deviation. Range equals max, mean the range quantifies the variability by looking at the range covered by all the data. The range covered by the data is the most intuitive measure of variability. The range is exactly the distance between the smallest data point and the largest one. IQR measures the variability of a distribution by giving us the range covered by the middle 50% of the data. The use of IQR equals Q3, Q1 as a measure of spread is therefore particularly appropriate when the median m is used as a measure of center. The 1.5 criterion for outliers in observation is considered a suspected outlier if it is below Q1-1.5 or above Q3 plus 1.5. The IQR can be used to detect outliers using the 1.5 criterion. Outliers are observations that fall below Q1-1.5 or above Q3 plus 1.5. The combination of all 5 numbers is called the 5-number summary and provides a quick numerical description of both the center and spread of a distribution. The range covered by the middle 50% is IQR equals Q3, Q1. Box plots are most useful when presented side by side for comparing and contrasting distributions from 2 or more groups. The 5-number summary of a distribution consists of the median, the 2 quartiles, and the extremes. The 5-number summary provides a complete numerical description of a distribution. The median describes the center, and the extremes and the quartiles describe the spread. The box plot graphically represents the distribution of a quantitative variable by visually displaying the 5-number summary and any observation that was classified as a suspected outlier using the 1.5 criterion. Properties of the standard deviation. It should be clear from the discussion thus far that the SD should be paired as a measure of spread with the mean as a measure of center. The standard deviation rule Approximately 68% of the observations fall within one standard deviation of the mean. Approximately 95% of the observations fall within two standard deviations of the mean. Approximately 99.7% of the observations fall within three standard deviations of the mean. For symmetric mound-shaped distributions, the standard deviation rule tells us what percentage of the observations falls within 1, 2, and 3 standard deviations of the mean, and thus provides another way to interpret the standard deviation value for distributions of this type. The explanatory variable. The variable that claims to explain, predict, or affect the response, and the response variable. The outcome of the study. Role type classification. Categorical, explanatory, and quantitative response. Categorical, explanatory, and categorical response. Quantitative, explanatory, and quantitative response. Quantitative, explanatory, and categorical response. Box plots are most useful when presented side by side for comparing distributions of two or more groups. C greater than Q. In order to summarize the relationship between two categorical variables, we create a display called a two-way table. C greater than C. The relationship between two categorical variables is summarized using data display, two-way table, supplemented by numerical summaries, conditional percentages. Conditional percentages are calculated for each value of the explanatory variable separately. They can be % if the explanatory variable sits in the rows, or column % if the explanatory variable sits in the columns. C greater than A. Q greater than Q. Scatter plots describe the overall pattern of the relationship. We look at its direction, form, and strength. The direction of the relationship can be positive, negative, or neither. Q greater than Q. Q greater than Q. The form of the relationship is its general shape in a scatter plot. The strength of the relationship is determined by how closely the data follow the form of the relationship. Strong or straight line, weaker or more scattered. Data points that deviate from the pattern of the relationship are called outliers. The correlation coefficient is a numerical measure that measures the strength and direction of a linear relationship between two quantitative variables. The value of ranges are from -1 to 1. The closer the value of R gets to 1 or -1, the stronger the relationship between the two variables. The slope is the change we would expect in the response variable for an increase of 1 unit in the explanatory variable. Positive slope. A positive slope of 1.0 for the regression line means that every change of 1 unit in the explanatory variable leads us to expect a change of 1 unit in the response variable. The slope of this line is negative, since b equals -2, negative slope. Extrapolation is prediction of values of the explanatory variable that fall outside the range of the data. Since there is no way of knowing whether a relationship holds beyond the range of the explanatory variable in the data, extrapolation is not reliable and should be avoided. A special case of the relationship between two quantitative variables is the linear relationship. In this case, a straight line simply and adequately summarizes the relationship. When the scatter plot displays a linear relationship, we supplement it with the correlation coefficient. The correlation is only an appropriate numerical measure for linear relationships and is sensitive to outliers. Therefore, the correlation should only be used as a supplement to a scatter plot. The most commonly used criterion for finding a line that summarizes the pattern of a linear relationship is least squares. The least squares regression line has the smallest sum of squared vertical deviations of the data points from the line. Because of the possibility of looking variables, we adhere to the principle that association does not imply causation. A looking variable is a variable that is not among the explanatory or response variables in a study, but could substantially affect your interpretation of the relationship among those variables. Whenever including a looking variable causes us to rethink the direction of an association. This is called Simpson's paradox. Including a looking variable in our exploration may help us to gain a deeper understanding of the relationship between variables or lead us to rethink the direction of an association. When performing EDA, we should always use visual displays plus numerical summaries, describe the overall pattern and mention any striking deviations from that pattern. Interpret the results we got in context. When examining the distribution of a single variable, we distinguish between a categorical variable and a quantitative variable. The distribution of a categorical variable is summarized using display, pie chart or bar chart, numerical summaries, category percentages. The distribution of a quantitative variable is summarized using inference, drawing reliable conclusions about the population based on what we've discovered in our sample. Probability is a mathematical description of randomness and uncertainty. It is a way to measure or quantify uncertainty. Another way to think about probability is that it is the official name for chance. Classical methods are used for games of chance, such as flipping coins, rolling dice, spinning spinners, roulette wheels, or lotteries. Classical probabilities can also be used for more realistic and useful situations. Probability is a way of quantifying uncertainty. We are interested in the probability of an event, the likelihood of the event occurring. The probability of an event ranges from 0 to 1. The closer the probability is to 0, the less likely the event is to occur. The closer the probability is to 1, the more likely the event is to occur. There are two ways to determine probability: theoretical and empirical. Theoretical methods use the nature of the situation to determine probabilities. Empirical methods use a series of trials that produce outcomes that cannot be predicted in advance. The law of large numbers states that as the number of trials increases, the relative frequency becomes the actual probability. For any event A, 0p1, p equals 1, that is, the sum of the probabilities of all possible outcomes is 1. The complement rule p equals 1p can be reformulated as p equals 1p. That is, the probability that an event does not occur is 1 minus the probability that it does occur. In probability, OR means either one or the other or both. P equals P. It should be noted that there are some cases where it is simply impossible for the two events to both occur at the same time, in which case we don't have to worry about the possibility that both occur when we try to find P. Two events that cannot occur at the same time are called disjoint or mutually exclusive, do not overlap. Example, one person can have only one blood type. The addition rule for disjoint events. If A and B are disjoint events, then P equals P plus P. P equals P. If events A and B are disjoint, they can never happen together. In other words, the event A and B can never occur, and thus P equals 0.
The idea of disjoint events is about whether or not it is possible for the events to occur at the same time, usually random pick out of large population. The idea of independent events is about whether or not the events affect each other in the sense that the occurrence of one event affects the probability of the occurrence of the other. The multiplication rule for independent events: if A and B are two independent events, then P equals PP. 3 people are chosen at random from a large population. What is the probability that all 3 have blood type B? We'll use the usual notation of B1, B2, and B3 for the events that persons 1, 2, and 3 have blood type B, respectively. We need to find P. Let's solve this one together. Independent because they were chosen at random from a large population, so use the multiplication rule of P and P. The complement rule, P equals 1P, together with the multiplication rule, is extremely useful for finding the probability of events like at least one of in several repetitions of a random experiment. Note that when we evaluate the conditional probability, we always divide by the probability of the given event. The probability of both goes in the numerator. The above formula holds as long as P greater than 0. Since we cannot divide by 0, in other words, we should not seek a probability of an event given that an impossible event has occurred.